Welcome to the Py database track. Alexander Hendorf. We talk about data mangling with mongoDB the right way. Thank you, Alexander.
Thank you. Thank you. Yeah. Hi, everybody. My name is. Oops. My name is Alexander. That far I know. IT is my second career. I used to work in the music business in the 90s, techno, house, vinyl, and we ran into an administration problem, and I had to learn programming. And I always loved data and doing stuff with that. So a few years ago, I founded the Mannheim, like our local Mongo meetup group. I just became a mongoDB master this year. Also, I'm certified Mongo DBA. And for the Python community, I work on the EuroPython program work group as program chair, and like to speak about Python and MongoDB and share knowledge and stuff. And today we're going to talk about data mangling in MongoDB. So that's basically MapReduce and the aggregation framework. So I'm going to take you, and we are going to have a lot of code examples. You can also download them later. So I'm going to introduce you to the aggregation framework, the pipeline model, operators and stuff, and also have an extra session which is brand new just for PyCon Italy, how we can boost the performance on that. Finally, a summary and some redemption. And since yesterday, I don't know whether you've seen it, I'm heavily inspired by programming, classic programmer paintings on Twitter. So I made one up for today. As you can see, it's also in Florence, which is nice. So let's bring everybody up to speed and just like check on the terminology. So document-based database. So we store documents. Documents are like a JSON-like object. We don't have schema enforced. Of course, we have some schema because it's not our taxes, it's schema. We store these documents in collections with it's basically like we call a table in relational database world, and multiple collections make our database. And basically the best physical representation I found for document-based storage is like a drawer like this. We can imagine the whole thing as a database. The drawer is our collection, and the cards are basically our data, the documents we store. And I'll show you a quick example of a document, a typical document we're going to work with today for the examples. You see we're working on a complex data set, but it's not super huge. It's like 45 gigabytes. But you're lucky we're only going to concentrate on like this. It's a collection from iTunes music store. It's the playlist, the album, singles, and we have an info block, which is basically like the album information, the artist, title, and we have a children's array with the individual songs on that album and release. And it's a nice example for like having data from an outside source where you're not really in control, where you cannot like say, I want the data the way I can digest them best, but I just get data and I have to work with it. So MapReduce. Many people, when they start MongoDB and they come from university or they see a lot of YouTube talks, they immediately tend to jump to MapReduce because MapReduce is the mother of big data. So who's familiar with MapReduce? Okay. So then let's bring everybody up to speed. MapReduce is basically a very simple algorithm, and it's basically the algorithm that built the Google search engine. As input, we have many documents. Could be anything, web pages, whatever. We just get the data in, and there's like a map phase. And the map phase basically is a filter and sorting. So basically, we take the contents from our document, and in this very simple example, we just emit tuples with like the words we find in our document. So For example, like hello world is hello one world. Oh, there's another hello, so another tuple, and then we, oops, I'm sorry. So, oh, there's something wrong. Okay, let's try here. That's better. Sorry for that. We map the tuples and we send them to our reducer, which basically is just like summing up. So we see here, hello, we have now hello 2, world 1, Peter 1, Parker below there. So oops. Okay, this is just like a little different representation. So we have, because the big advantage of MapReduce is we can scale the processing of our data. So these are all the servers. We take the documents, we take our data, spread them across many, many, many servers. So we have like many workers on servers, and then we emit our tuples to some other servers, same servers, depends on the setup, and then they do like summarization, accounting, and all the stuff. And as you see, it's already also sorted out which tuples go where. That's why I highlighted the 2 hellos. They all go to the second server here. But we don't want to go into more detail here. So a very simple map reduce function is just like we take the document and we just get the artist name, which is stored on this path, and we just emit the artist name tuple, and our reduce phase is just like taking all those tuples and summarizing everything. And this is time for our first demo. So this is a Python notebook I've prepared. It's also on GitHub in the previous version, but I'm also going to push this version up. So basically, it's just like a connection to our database, and I've prepared this because I wasn't sure about the internet connection here and how stable it is. So I've pre-run it. Again, we have a mapper, which is basically just stored in code. So because basically we're just like sending this as text, as JavaScript text to our mapper. And we have the reduce function, which is just like the same as before. We just wrap it, so we can send it JavaScript code to mongoDB, because mongoDB internally works with JavaScript. And we take all the tuples we receive and sum them up. And then finally, we send everything. We want to send all our results to a new collection, and we can do that here. So basically, there's only one part, the result part. Just like go to our database, playlist collection, and run MapReduce with the mapper and the reducer code we just stored above. And if we ran it, we would find out that in our dataset we find 523,512 artists, unique artists in our dataset. And the whole thing took like 6 minutes. And if something takes like 6 minutes, that's like forever today. So it's totally unacceptable. I can't wait 6 minutes. So what can we do? That's like, what's the problem here? So let me switch back. So our mapper provided a map reduce phase, and we got some output, and it took us 6 minutes. And why is that so? Of course, as you probably remember the slides before, we did not split our dataset in any way. So the biggest power of the MapReduce algorithm is splitting the income data on many, many servers, and we just run our MapReduce algorithm on one single server storing our mongoDB database. So we cannot really use the major advantage of MapReduce, although it's handy being built in. So basically, for us, at the current state, we know MapReduce is like our evil stepmother and not the mother of big data in MongoDB. So, but what else is there? There's the aggregation framework, and that's built in MongoDB. And it's very often overseen because people immediately jump to MapReduce, and it's a very powerful framework. It's was released with MongoDB 2.2 in 2012. It's a framework for data aggregation, as the name points to. It's designed in a straightforward fashion. So we basically build a pipeline and transform our data from one step to the other until we receive an output. And the MongoDB documentation describes it like this. So we have our orders document. We do a $match, which is fine. So we match on, what do we match on? Something. I'm guessing on the, yeah, we match on something. I don't see it. So we get, for example, like 3 documents back, and then we group them by our customer ID. So we have 2 documents with a customer ID. We group them and sum them up of the amount they purchased with us. So very classic example, and we get 2 documents back. This is very technical. I really think I always try to have people imagine it like a relay race. You know, like from relay race, you know, probably know from the Olympics. So the match phase is basically our doggy. So we can say, hey, doggy, get the baton. This is like the data. Then we pass on the baton to, for example, a group, which is our fox, doing something smart with our data. And then we can present it nicely and pass it on to a project, which is represented by an ostrich here. So that's the vanity factor. So let's start with a simple example. This is again the simplified version of the document we were working with. So we have on top release information about the release, album name, artist, when it was released, and chosen songs. And let's build our first simple pipeline. So we're going to store the our pipeline just like to a simple list, just like a list. And in this list, we pass objects, and they always start with one of these aggregation operators. So it's a $match, which is a where clause from SQL. So for everybody who's used to working with relational databases, I put some hints here. So we are looking for some artist we have stored in another variable. And then we just get all the documents from that artist and project them, and just project the release name. And that's basically it. And then we sort the release name ascending. And of course, the biggest question now is, who's the artist? And it's Taylor Swift. Why? I see it in your face. Why Taylor Swift? This guy doesn't look like a Taylor Swift fan, and I'm not. But I'm from the music industry. It used to be, or still have clients in the music industry. And last year, Taylor Swift wrote this great blog post. Apple wanted to launch his new streaming service, Apple Music, and they asked the independent labs, yeah, we have a trial period, and we don't want to give you any money for the trial period. And then Taylor Swift wrote this blog post pointing out, I don't get any iPhones for trial periods for free, basically. And Apple reacted within like 24 hours and said, yeah, of course we're going to pay. So that's why she deserves to be here. So let's jump to our first example. So we're going to do a demo about very simple aggregation pipeline. We're going to do a match, find some data, project them, sort them, and produce some output. Let's see what happens. So just like a quick check. Okay, our database connection is working. We found 48 releases for Taylor Swift. And here we just built the same pipeline as just showed on the slide: match, project, sort. And then we store the result in a variable and print out how many documents we found. So basically, this is the very same as we did before with our find. So let's do that. So, okay, cool. Our aggregation pipeline also found 98 documents. Looks good. So then let's have a look at our data set we just received. And oops, this doesn't work. Why? Why doesn't it work? It does not work because mongoDB gives you back a cursor. So it's just like a pointer to the data you're going to receive. And above, when I just did like this simple print for how many documents we received, and I took just like the len of the list, our cursor was already exhausted. So after this step, it was empty. So remember, if you want to work with your data, also store the data you receive back from the cursor in another variable if you want to do multiples, use it more than once. So let's do it again. And here we get our releases back. This is what our data looks like. So we just, as you see, we only get release names back. That's it. And now we're going to do the same. And hello? Yeah, oh, sorry. That was too quick. So here we see all the releases we have wished for, all the albums. And few of you will already notice, oh, we have duplicates. Why? And we're going to come to that in a second. So go back. So as I just showed you, there's like big trap. MongoDB returns a cursor. Once it's completed, it's empty. So store your data to a variable if you want to reuse it. And to give you a little bit more overview, what we have at hand, these are like the aggregation stages we have, and basically they're brothers and sisters in the SQL world. $match is aware, having, sort, order by, quite obvious, limit, it's quite the same. Project, this is select, so that's sounds weird, but it's very familiar. Select. Group is group by. Unwind is some kind of a join. That's a very unique operator. And then now, for the latest version of MongoDB, yes, we do have lookups, which is a left outer join, which is quite a surprise. So then we have some more MongoDB unique concepts, or like redact, skip, which is also like skipping records, quite obvious. Geoneer for geolocation, and out for storing some stuff to a new collection. We can also sample our data set. So basically this gives us just like random samples from our data set, which is really nice for testing new code. An index text is not really an aggregation thing, in my opinion. It's more like a performance operator. Tells you how often indexes were hit for the time your MongoDB instance is up and running. So if you close it down, you start with 0. So it's different. So let's go and move to our next example. And now let's do a group. So let's work with the artist name. And name is the title of the album, or playlist, or single. And we want to do a grouping. And how can we group with MongoDB? So I'm only highlighting the stuff which is new in our pipeline. The others we already seen. Match, we find everything by Taylor Swift, and now we group everything by the release name, which is stored in info name. And then we want to basically see how many duplicates do we have? How often do we find per album? 90. 1983. No, it's 1989. And we do this with a sum over 1, so we don't have a count in mongoDB. We do sum over 1. And let's just show you grouping and sorting by multiple attributes. Okay. So here's our pipeline. Match, grouping, and then we just project and sort as we did before. And here we go. And also this nice table representation. It's something, it's just like an HTML table. Don't worry about it. It's just like a wrapper to present the data a little bit more nicely. So we see her release 1989 we found it 4 times in our data set. And why is that so? It's like an international release. It's just like released by multiple companies throughout the world. And of course, each release from across the world gets a unique new ID. That's why we have it more than once in our scraped data set. It's a very simple explanation. So what else can we do? Let's see. We can also do use sort and limit. And here we see. So what do we expect? We now sort by count descending and the release ascending. So count descending, release ascending. Yep, looks fine. So let's do the same again and sort by release ascending and count descending and see what we will get. And this is obviously not what we expect. And why is that so? Somebody, why does this sort not work in Python? Yeah, of course, we pass in a dictionary, and a dictionary is not sorted. So basically, it's just like we're having some random order. I was lucky, it worked on the first example. Sometimes it's the other way around. So Python dictionary does not maintain the order of its attributes. So we have to come up with something else. And of course, there's a solution. It's let's pass in a list, or like in this example, it's a son. It comes with mongoDB with a Bison library, and we just pass in cursor. Just pass in a list and a tuple with release, ascending, count, descending, and this way we can make sure we get the data in the sorting order we are looking for. So looks nice. Okay. Now we have the releases and count. Okay. So we're already one step ahead. We can do grouping now. We've learned Python list. We use Python dictionaries. They're not in a guaranteed sorting order, so we need to use something like a list when we do sorting, or use anything which is like where the order is important. So next question is, how can we work with this nested stuff? Like, this is like making people very often really crazy. We have like basically a parent level. There's also like info for the album release stuff, and then on the album release we find the children, which is a list. And we cannot really access it directly because it's a list. We have 1 to n objects in our list, and how can we actually work with the artist and the title of the song? And this is where this crazy unwind operator comes in, because unwind is basically flattening everything out, and this is a very unusual concept if you come from relational databases. So I've made up another example. For example, we have here Mother Dorothea, and Mother Dorothea has 6 children. And two of the children are really famous. That's the Brothers Grimm at the beginning. And what happens if we unwind that list? Basically, we just like get this back. So we keep the mother, the children. As now, we didn't change the schema. We just flatten it out. We have no longer have an array. We just have gotten back multiple documents. So basically, it's like we have mother hippo with her children, and then we have 3 mother hippos and 1 child. And let's show how this looks in code. And while I am switching all the stuff, this sounds like a really expensive operation, but it isn't. Actually, I had one example where I got the data, the list, to my code and to use the loop to work with to get what I wanted, and then performance was really getting bad, and I looked for ways to improve, and actually like the aggregation framework saved me here. I think it was like 1,000 times faster than doing it in the code and pulling the data in and getting it in code. So again, just like the same as we've seen already, we just like added this extra unwind, and now we're going to unwind the info children list, which is basically a representation of the songs. And then we're going to project the songs. So what do we get? Yes, it's a list of all Taylor Swift songs. Wow, many songs. So, and again, a little example of the inner mechanics, because it's to get it in your head a little bit better. So I just took one playlist from our dataset, one document, and unwind the children's array, and basically this is what we get. It's all the same playlist. We can see it from the Adam ID, and then the album name is the same. Album name here is the same. It's a Fearless Platinum Edition. Wow, and we have all the children's really accessible as objects. So I've mentioned these before: skip out, write to a document. Oops, geoneer, work with geospatial data, redact. From something like a doorkeeper, you can limit the output of subdocuments depending on the contents of your documents. Probably could set an attribute management only and set something. I've never seen it actually. And then we have the new stages: lookup for left outer join, sample to get some random documents, and index stacks to inspect how often we hit our indexes. And of course, we can do more. We also have accumulators like min, max, average in the aggregation framework, and let's work with that. So let's go back to our document. We're back on the release level, and we have outside data, and Apple is really in a good mood and gives us 2 release dates. One is basically a string, and the other is an ISO date. And let's see how we can work with that. So we're going to have 4 examples in a row now. Later. Thank you. So 4 examples in a row. We're going to do a min-max, which is basically we take our ISO date, pass it into $min and $max, and we expect like the lowest and the biggest value from our playlists. The next one is first last, which is really handy if you work with big data sets, and or you have your data in a sorted fashion anyway, because we could also, like, instead of using min max and basically going through all our data set and looking, hey, what's the minimum, what's the maximum, we can also like provide it our data set is sorted, we can just like get the first and the last document and get the same results. And if it's a huge data set, this can be more effective. Also, if you have probably a special sorting order you made up yourself also. And two more examples. We also have date operators to work with dates. So from our release date, epoch, which is an ISO date, we can also just like get back the year from that date. And if we want to go a little bit closer, we can also build a multi-key index. So we can get a new ID from the year and the month. And probably you're in the grouping, you're a little bit confused about why is there always like an underscore ID in a grouping, and that's a convention. Basically, underscore ID in a group stage, we always need an underscore ID. It's our grouping key. And we also see an example where we have an empty grouping key later, but this is like important. So, and we can build like our grouping key also of multiple attributes. No problem at all. And then we just count everything. So let's see it live. So accumulators, date operators. So this is our pipeline. First example, we just getting like a classical min-max from our data set. And this is the result. So Taylor Swift was active from 2006 to 2015. Great. And then let's do the same. First, we sort our data, and then we just pull the first and the last document. And since we sorted by just like the same, or like in our case, like the text representation of the date, we expect to get the same result. And yes, we do. We have, of course, we get the text representation of the date back, but it's also like 2006 to 2015. So that was easy. Now let's do a grouping. Because I'm talking so much about Taylor Swift, I'm getting more and more attached, and I want to find out when's the next album due, and I'm trying to get some insight from analyzing her frequency and releasing stuff. So, and as we expected, in this case, we just pull the year back from our release date. We get a minimum and a maximum date. And let's do the same in the grouping. And we see, oh, yes, she's really busy. And let's do the same and just like add another key to our grouping key, which is basically the month. And now we see, wow. Yeah, she's really taking a break, isn't she? So now we know how to work with dates, accumulators, and since we're tired of Katy Perry, I ask myself, who's the nemesis? Who's her arch enemy? And I asked Google, and Google told me Katy Perry is her arch enemy. So, and I'm wondering, I cannot decide. I'm really getting attached to all these girl bands now. So I'm trying to find out who gives me more value for my money. So who gives me more playtime for my 99 cents? And let's find out. So to find both artists, we just like pass in another, it's like $ist in our match. So we're going to match everything. If the artist name matches to the artist or the nemesis stored in variables, it's like basically the same than doing like, we could also like use $or and say, okay, artist name is either this or this. But $in is much more effective because in $in we only have to look at the attribute once. In an OR, and even if it's like a complex search, we have to look at the artist like from design multiple times. So $in is usually more effective or efficient. And also it supports rigid. Oh, thank you. How can we accomplish it? Well, oh, no, sorry, took a switch to demos. And let's do this. So we have our nemesis. We now do the same grouping, just like to find out. She has a really similar active period. Taylor Swift, Katy Perry, very similar active period. Although Katy Perry is already taking a break since almost 2 years now. And we're pulling this document, which is really deep down, buried here in an assets array. That's a playtime, where we're doing 3 unwinds to really flatten our data set. So get all the documents from both artists and flatten our data sets, and then we just do some cleanup. Don't worry about it. And then we just take our $AVG for taking the average for our playtime duration, which is actually stored in seconds. And here we just do a little rename to make it look a little bit more nicer. So Taylor Swift gives me more music for my money, so that's really okay. Wow. So it's a really bad way to look at music like this. I'm just kidding. So we've taken like 3 unwinds and averaged everything out. So if you're not sure how your aggregation work and how you probably can make it more effective, you can also use just put explain on the end of your aggregation, and mongoDB will give you something back on index usage, how it will process your query, and it's really good if you're looking into optimization of your stuff. So I have to speed up a little bit. So now we're going to work with text. The question is, can we work with something like this? Really ugly, price formatted, dollars, non-breaking space, number, but stored as a string, and it's from an outside source. Can we work with something like that? And of course we can. It's getting a little bit more complicated. So let's start here. We're taking this attribute, and I'm just taking like a substring. It's like as in JavaScript. So substring takes the first 3 characters, and we convert them to lowercase. And then we do with $CMP, we compare, is it USD lowercase letters, and store this to a new attribute is USD. And we do this in a projection phase. It feels always more like something like for a grouping, but we do it in a projection phase, and then we do something really strange. We do a match on is USD 0. Feels wrong because like 0 is no, it's false. But the comparison operator is really smart. 0 equals 0 difference. That's the best way to remember it. And it gives you -1 back and 1 back, depending whether the value is bigger or smaller. And that's really handy. So basically, you get a lot of more information, and the best way is to remember it like 0 difference in this case. And let's do a quick demo. So again, our string operators. And let's just like run it, see what happens. And this gives us a nice list back of everything we have, all the prices of all the albums, and I've just grouped it by the artist names. So how much time do we have left? Like 5? Okay, so I have to skip a little bit. 5. Have we got 10? Can I have 10? Yeah, okay. You want to have 10? Or you want to go? I've done 10. Thank you. Okay, then I can give you one more example. So we've introduced to all the accumulators, like sum, min, max, first, last, push, add to set. We haven't covered yet. There's also a lot of expression operators, Boolean operators, set operators. Just have a look at the MongoDB documentation. It's really well written, many code examples. It's very accessible, I think. And let's do something a little bit more crazy. Let's do a mapping. The cool thing is it's just like the map function in Python. So what do we do with, we have already the data from before, like in US dollars, and now we're interested in, hey, I'm interested in what's that in euros. So I've changed the dollar exchange rate in a variable, and also we have a grouping. So we have an artist, and then a list with all the prices lined up. And our map function is going to take this, the price, and map our function here to each and every element of the array. And this is basically just like a multiplication by the value we get from the array by the value here. And let's jump to the demo. And yeah, so this here. So this is our mapping, something back, and this is like pricing array we get back. We haven't done anything yet. This is just like as before. And now let's add our mapping function here. It's a bit nested. You have to more like think it's not. We don't think as like the stuff like running like a for loop. Think more like how can you nest stuff. It's easier because we don't have loops, and that's it. That's our euro pricing. And then a really quick example. We can also use like dollar lookup. So we can look up data from another collection, and our collection is exchange rate, and exchange rate is really simple collection. That's the currency code, and we store the rate, and it's a very simple database with like 200 objects, and let's do that here. So we take dollar lookup. We say, get it from the other collection, store everything we get from there. It's left outer join, so if we have multiple hits, you get a hell lot of documents back in an array, and store it to a new field, or like what's the key field we're matching on, and how do we want to name it. And this is what we get back. And we can even take this one step further and instruct our projection, our map function a little bit, give it more instructions. We can also instruct our mapping on, please take the first element from the array we got back from the other collection, because I know there should be only one exchange rate. So I can say, yeah, take the first element back, take the object, and take the first thing, and this is the rate I'm looking for. So we can speed things up. So, and that's basically it. So so yes. So now we know a lot about the performance of the aggregation framework, but we still see we're limited to one server. We can run our aggregations on, and we've seen MapReduce, and what we know from MapReduce, the key is scalability. Like, take all the work and put it on many workers. And now we're wondering, can we do this with our data in MongoDB? You probably heard about the Hadoop connector or Spark, but wouldn't it be great if there's something we know from our MongoDB ecosystem, something you know well as MongoDB? And there's like, this is where we stand with this data set. We have one server, one database, collection with a hell lot of data. And typical use case or a typical scenario is having a replica set. So we have one master, primary, and copies of just like exactly the same data on secondaries, but that's copies, and it's not really helping. If you think like, to scale the work across like these three, there's a lot of extra overhead and probably doesn't feel well. So what else? What else could we do? So if we cannot scale horizontally, what about scaling vertically? Let's so take our data and split our huge data set into smaller chunks and split the data across multiple servers, in our example like 4. And that's called sharding, and it's built in MongoDB. You can build a shard and build a sharded cluster on multiple servers, and then, of course, we can harness the power of each and every server in our shard. But if you've looked at MongoDB, you know like MongoDB doesn't really need many resources on CPUs, and servers have a lot of CPUs nowadays. So basically, they're all bored. For MongoDB, I/O and RAM is essential. The more RAM, the better. So is there another way? Because I'm only want to have a one-day aggregation on my huge data set because my client's really pushing me, I need the data. So is there a faster way? I don't want to get like tons of new servers up and get all this extra infrastructure. So is there another way? Wouldn't it be great if I could run everything like on one server and utilize the power of my multiple CPUs and I/O, because I can go just like to a cloud service provider and they have machines with like 40 cores. I can have like 120 gigabytes of RAM, just like that, and I can have a lot of I/O. I can basically build my one big super machine there with some configuration in my console. And this technique is called micro-sharding. It's you take one server and utilize all the CPUs. And it's a little bit more detailed. So we have the CPUs, a lot of RAM, high IOPS. Yeah. So basically the formula is as much RAM, much more RAM is better. But of course, you don't need more RAM than your data set plus the indexes, because this is what we're going to want to store in RAM. Take one shard per CPU, and that's it. That's the basic idea. If you want to look a little bit closer into it, there's a gist from John Page from MongoDB in the UK. I included a link in the slides. There's a whole tutorial how to set it up, and I did it actually a little experiment last night. So I'm going to show you the results later. And basically we can accomplish with micro-sharding on just like one single machine times the performance plus of times the shards. So if we have like the biggest box from Amazon, 40 cores, a lot of IOPS, lots of RAM, we can have a performance plus of factor 40. We can run our code 40 times faster. And since I told you so many bad things about MapReduce before, bad stepmother and stuff, of course, the same applies to MapReduce, because the bottleneck is I/O, RAM, accessing the data, and also with micro-sharding or sharding in general, we can also like get more performance for our MapReduce algorithms and improve them. So let's do a demo. It's not a demo, actually. I've pre-run it because it takes a little bit more time to do than before. So just wanted to show you the code and the results. So this is the pipeline we know before. We just getting the artist names in and count them. So And for example, like we have a replica set symbol server, and I have to point out this is not super lab surrounding. I just took 2 servers. They only have 2 SSDs, 8 cores, and they also run some other stuff. So this is not like the best. It's just like, but I just wanted to get, okay, is this working? Get a hint in the right direction. And I got one. So on the replica set, single server. Our aggregation took 1 minute and 48 seconds. When I used the machine and built a micro shard, it took 34 seconds. This was not like the factor like CPU, but I guess like only off-the-shelf SSDs. So we can do better on IOPS, but you see the direction we're going. So we can utilize and harness the powers of the servers we have anyway much better. And the same applies for MapReduce. So as we know before, yes, this is the game over. As we know before, it took 6 minutes, and with the micro-sharded solution, it took only 56 seconds. So this was a big scale up, even like on not super surroundings. And as a last example, also pre-run, who gives us the most playtime on the store, yeah, because we're still pricing sensitive. So we're getting now the duration, which is really nested deep behind with many unwinds for our complete data set, which is like 20 million songs. So I pre-ran it, and on a single machine it took 4 minutes. And on the sharded version I could narrow it down to 56 seconds. So this is actually working, and because the only thing you're most interested in, who gives me the most value for my money, I didn't do an average as before. I did a sum, who has the most playtime on the store. So this is like a hell lot of hours on various artists, and the first in Ella Fitzgerald is basically there's 1,036 hours of Ella Fitzgerald music on the store. And this is where we come to an end. Stop. So this is where we come to an end. The end. So little advertisement. As I told before, I'm also working on a EuroPython organizing. So we have a second call for proposals for Hot Talk-X, first week of June. So if you want to submit something, but really nice and techy, do so. And of course, we will happy for everybody coming to EuroPython. Here are my details, the slides you can download from here, and I also included a link to John Page's tutorial. Thank you.
Okay, we have few minutes for answering questions. Any question?
Okay. Yeah. During the unwind, I have some limits for the dimension of the new database, or
no, that's the document limit. Also applies for aggregation pipelines. It's 16 megabytes,
okay,
which is a hell lot of text. And actually, I've never ran into this. Also here, like imagine, like we took our whole data set and took this really nested thing. We didn't run into problems. But even if you do so, there is an option. You can also use disk as cache, which sounds bad too. I can have to use more than 60 megabytes. Can I use my disk as cache? But you can do so, and even run to avoid the problem if you ever run into it. Yeah.
Okay, thank you.
Okay, thank you.
Yeah. Thank you.